5 different face detection methods in Python. OpenCV's Haar Cascade based face detection, Dlib's Hawk plus SVM based face detection, OpenCV's deep learning based face detection, Dlib's maximum margin CNN based face detection, and Mediapipe's glaze face detection model. Not only are we going to learn how to use all of these 5 facial detection methods, but we are also going to look at some pros and cons of all of these and when to use which detection model. Let's get started. So for this tutorial, we will be following along this Jupyter notebook. And for that, you need to have 3 libraries installed: OpenCV, Dlib, and Mediapipe. All of these can be installed using pip. So pip install OpenCV contrib Python will install OpenCV, pip install Mediapipe will install Mediapipe, and pip install Dlib will install Dlib. Now Dlib is a bit of a hassle to install if you're using a Windows machine. So for that, you first need to have CMake installed and configured in your path. And you need to also have a C compiler installed. And even then you can face some issues, which I did face when I was installing Dlib, but I then went on and installed a pre-compiled Dlib library, which you can do once you create a new environment for that. So I have an environment, root environment is in 3.9 or 3.8 Python, and I created a separate environment with Anaconda, Python 3.6, and then I installed a pre-compiled Dlib library using conda install Dlib, something like conda install force Dlib. I think it will be available if you just Google conda install Dlib command. And there's another version, another pre-compiled Dlib version, I think, that you can do with get with pip, is pip install Dlib, I think equals 19.8.1. I think it's that. Anyways, so there are 2 ways to go about it. You either install a pre-compiled Dlib library or you install from source. So, but when you use a pre-compiled version, there is a bit of con, there's a bit of a disadvantage in that, and I'll tell you later about it. So now let's import all of these libraries. So the first algorithm that we're going to go over is the infamous OpenCV's Haar Cascade based face detection. This is the most popular and the oldest method here. And if you're working with OpenCV, most of the people just use OpenCV to use this algorithm. Anyways, and it's pretty simple. All you need to do is call this command cv2.cascade classifier, pass in the model name. So I have this model Haar Cascade frontal face default.xml inside my models directory. You can get that directory once you download the source code. So the model is present here, and I'm loading up the machine learning model in this object. And once I do that, you will see that it's displayed here. So this is the loaded Haar Cascade model. Right now I'm using the frontal face model. There are other models too, but the most common one, and I think the most effective one, is this, the frontal face. There is a cat model too. There's a pedestrian detection model too. But normally nobody uses those models that often because they're pretty weak. And the most common one is this frontal face detection model. And that's loaded up. Now all we need to do is call this method, cascade classifier.detect multiscale. We pass in the image, we pass in some other variables, and the face detection is done in this single line of code. And as you can see in the code here, what I'm gonna do is I'm gonna pass in the image, I'm gonna just extract the height and width, and then I'm gonna convert the image in grayscale, and then I'm passing the image here. I'm passing the grayscale image here, and then I'm specifying some variables here, and then I get the results object. Now this results object will contain all of the face detections. So now what I'm going to do is iterate over each of the detected faces. So when you do face detection using Haar cascades, what you get is first you get the x1, y1 coordinate. These are the top left coordinates of the face, like here, and then you get the width of the box. So you get the width of the whole face. If the face is large, you get a larger width and height. And similarly, if the face is detected far away, if the person is standing far away, then the width and height would be a lot smaller. So these are the width and the height. And if you need to draw a rectangle around the face using cv2.rectangle function, like here, you need x2, y2 too. So for that, what we do is we add the width to the x1 coordinate to get the x2, and we add the height to the y1 coordinate to get the y2 variable. So by doing that we can create the rectangle around the face RY. So this is what we are doing here. We're adding the box width and the box height onto the x1, y1 variable, and that way we have a box around the whole face. Now, if the display variable is true, I'm gonna put out a text face detected and the total time taken, and then I'm gonna display the plot with matplotlib. And if the display variable is false, and then I'm just going to return the results object, and I'm going to return the annotated image. Now, normally I set the display variable equals to true when I'm working with images. I want to display the results. But when I'm working with videos, I don't want to display a single image as a plot. I just want to return the results, so I can use cp2.imshow to display the video results. So now this is the whole workflow for detecting the faces using the Haar Cascade function. Now let's go over the variables here. But before I show you the variables, let me explain what Haar Cascade based face detection normally does. So essentially, these are Haar features. Like this is the edge feature for detecting the edges in the image. This is a line feature for detecting lines on the image. And there are other types of features too. So what happens is that we have a bunch of Haar features and they detect some sort of features on the image. Normally, they are designed in a way to detect facial features like eyebrows, eyes, nose, etc. So take a look at this example. What we have is an image with the face at the center. And this red box is actually a sliding window. And this box starts from the corner of the image and goes all the way to the bottom. And as this window goes across the whole image, there are a bunch of features called Haar features that are trying to detect some targeted features inside the image. So these are the features that they were trained on. So for the face, they are trying to detect the corners or the edges of the face, facial features like the eyebrows, nose, eyes, lips, things like that. So once these Haar features detect a lot of features that indicate a face is present, they'll tell the model that I found a face. And once that is done, that will be classified as a positive detection. Take a look at this. So the sliding window is going across all the way. And if I forward this up a bit, when it reaches the face, it will stamp it, telling it it's a positive detection. So that's one positive, and it's going to be another positive because that face, that arrow again falls on top of the face. And similarly, we'll see multiple detections for a single face because the whole box is sliding across and it's overlapping the face multiple times. So as you see, even if only a single face is present, it will be detected multiple times by this sliding window. And this is how this whole Haar Cascade essentially works. And let me show you another step here. So if I, forward this a bit, you'll see the sliding window starts at the top again, but this time with a wider box here. And if I forward this again, it's gonna repeat the same process again, this time with a bigger box. So this is how the Haar Cascade works. Generally, we have a sliding window, there are Haar features inside it, and that whole sliding window detect faces in multiple different scales, so that faces of different sizes are detected. And this is just a very, very short summary of it. In essence, there's a lot of other things that goes inside how the whole pipeline works. So if you want to read up further on how this whole thing works, there's a nice summary here of the Haar features in this OpenCV documentation, which will be linked in the blog post. So, and this is again a really short summary of this whole thing, how this works. Anyways, now let me introduce you to those three variables here. So this is the image, and then we have this min size and this max size. Now this min size and max size is basically telling the algorithm that faces with a size shorter than this should be rejected, and faces with a size larger than this should be rejected. So this way you prune out any undesired detections. So this is a way to get rid of false positives. Normally, when I am working with Haar Cascades, I don't tune these two variables, but they are nice to have if you want to prune out false positives. And then we have this image, and then there is this scale factor. Now, this scale factor normally controls how many times you want to shrink up the image. So this is how this looks like. This is an image pyramid in which we have a large image, and then we shrink it down, and then we shrink it again. So remember when I showed you the whole pipeline of how the rectangular box, the sliding window, goes across the image and then it gets larger. But this is something that the algorithm of the Haar features authors did in the original algorithm. They resized or they increase the size of the features. And this was a smart way to reduce competition and detect faces of different sizes. So if a person is standing close up to the camera or far away from the camera, the algorithm should detect the face. So, and we accomplish this by resizing the image at multiple scales. So this is what's happening here. If I do a scale factor of 10% by doing 1.1, that essentially means that I'm downsizing the image by 10%. If it's downsampling, and then there might be upsampling. So there are two ways to go about it, either to upsample the image or downsample it. And then we have this min neighbors. And this neighbor controls the false positive rate. And by setting this to 3, what I say, if only a face is detected 3 times, I'm only then going to consider it as a valid detection. So remember when I showed you the whole demo, a single face was detected multiple times. So I'm saying here, if a face is detected a minimum of 3 times, only then I'm going to consider it as a valid detection. If you see a lot of false positives, you can increase this number. And if you don't see detections where it should be, you should decrease this number. All right, let's test this out. And I'm going to initialize this function, and then I'm going to call it on a bunch of images. So all I'm going to do is read an image with cv2.imread, and then I'm going to pass in this image with the function I created above. The Haar Cascade detect faces image, the Cascade face detector which I loaded above, and display set to true. So let's run this. So for this face I have this result, and then the other one, and I have no detection for this one. And you see the reason is that the face is tilted like this. And when the face is tilted with OpenCV Haar Cascade, you won't be able to find faces. And this is a disadvantage of using Haar Cascades. And let's take a look at another image. And for this image, we have this face detected, but like this face was not detected, and there's a false positive here. Again, I might be able to get rid of this false positive by setting the min neighbor to a higher value, or changing the scale factor. By changing the scale factor, I increase the accuracy, but at a cost of computation. So because when the scale factor is increases, I looked at multiple image sizes to find the face. But at the same time, it would take a lot of time to take a look at different sizes of the image to find a face. So this is a trade-off which you need to be aware of. Anyways, as you can see, the Haar Cascade works fine when you have a face, a frontal face, which is the reason it's called a frontal face detector, right? Frontal face. The face should be looking at the front of the camera. But if it's sideways, if it's tilted like that, you won't find much success with the Haar Cascades. So that was our first detector. It's the most popular one, but it's the most basic one, and it's limited. Now the next algorithm that we're going to take a look at is Dlib's hog-based face detection. Now besides OpenCV frontal face detection, hog-based face detection can also detect faces oriented to the left side or the right side, and then the frontal face that is kind of like right, and frontal face that is rotated left like that. So this is sideways rotation, and then this tilt, left or right tilt. So these are some of the orientations that you can also detect by using Dlib's hog-based face detection. In fact, here is a demo of OpenCV's comparison with the Dlib hog-based one. So this is a short demo video which compares the OpenCV's facial detection, which is in blue circle, and the hog-based face detection, which is in rectangle. So as you can see, most of the time the hog-based face detection is correctly detecting the faces, whereas the OpenCV circles is giving false positives throughout, and it misses a lot of detections. And you can watch this entire video in this page. I'll probably link this to the blog post which we're creating. This blog post is actually by Davis King, who is the author of Dlib library. And this is the release post for the Hog plus SVM based face detection. And this has 2 parts. So we have a hog based histogram of oriented gradient based facial features, and feature detection. And then we have a classifier, SVM, support vector machines classifier. Now SVM is one of the strongest machine learning based classifier, and the Hawk features are one of the best features that you can get from the image. So normally when we are working with images for building a classifier or a detector, we don't normally work with raw pixels. So we first extract some features from an image. Now these features may be any features like SIFT features, scale invariant feature transform, very popular in OpenCV, or SURF features. But one of the best feature detection methods is HOG. And I'm talking about the time when the CNNs or deep learning was not the norm. The HOG features were used a lot. Now these are the HOG features. Basically, what we do, we just take a histogram of all the gradients of the gradient or the intensity changes in the image along with their orientations. So it looks something like this. Now this is a HOG map of a face, and this is a HOG map of this particular object. As you can see, it's sort of similar, this HOG feature map of this image. So it encodes the direction or the intensity changes of the major features in the image. So this is the HOG map for this, and this is the HOG map for the face. As you can see, these are the eyes. Probably you can make it out. This is the nose, this is the lips. Now this is what the HOG features are. Now combine the HOG features with one of the most effective machine learning algorithm called support vector machines. So when you combine these two, you essentially get a very efficient classification system. Now you have a classifier. Now when you combine this classifier with image pyramids, with a sliding window, you create a whole object detection pipeline. And this is what is happening in this facial detection pipeline. So to get this running, what you do is load up the facial detector by doing dlib.get frontal face detector, and then store it in this object HOG face detector variable. And then I'm gonna print it out here. So this is the Dlib HOG based facial detector loaded up. And then what we're going to do is just call this method HOG face detector, pass in the image, and then we have this upsample argument. Now this upsample variable upsamples the image. Remember when I told you about the image pyramids where you upsample or downsample the image in multiple sizes, so you can detect faces in varying sizes. So this is where this variable is useful. Right now I'm just going to set it to 0. And this is going to allow me to have a real-time, like speed on running on a CPU. And again, you can upsample, but you only need to do that when you have faces that are, like less than 80 by 80. So if you have an image where the facial size is less than 80 by 80 pixels, only then you need to upsample. Other than that, you don't need to upsample the image. Again, like I said, if you do upsample, it's going to cost you speed. And all right, so let's run this. But before that, let me show you the code here. It's relatively pretty simple. You only the extra thing that before passing calling the HOG face detector, you convert the image in RGB, because with OpenCV you load an image in BGR mode, and HOG because you're using another library called Dlib, and Dlib accepts an image in RGB format. So for that, what we do is reverse the color channel, convert from BGR to RGB, and once we have done that, we have an image in RGB, we pass into the HOG based face detector, and we get the results. Inside the results, we have bounding boxes for each of the face that is detected. So what we do is iterate over all the possible detections. We extract the X1, the Y1, the top left corner and the bottom right corner, the X2, Y2, and we can do that by calling bounding box dot left dot top dot right dot bottom. So bottom, so when we do dot bottom, we get the y coordinate value that is at the bottom of the image, and then for the top we get the y coordinate value that is on the top of the image. And similarly, bounding box dot left will give us the x coordinate that is to the leftmost of the image, and similarly the x2 will be the rightmost of the image. So this is how we extract the x1, y1, x2, y2 coordinates. And once we have done that, all we need to do is call cv2.rectangle function, passing the x1, y1, x2, y2 coordinates, and it will draw a bounding box rectangle on top of the face. So when that is done, all we do is just display the results or return it when we're working with videos, similar to the above function. Now that the function is initialized, let's test it out on a couple of images. So we have this frontal face here, and then we have another image. As you can see, this face is oriented like this, and still the detection is being done here correctly. And then we have another image. and yeah, so 0.44 seconds. And but as you can see, the face is not strictly detected. So the chin is missing out, this part of face is missing out because it's occluded by the hair, so the detector misses it. And let's test another image. And yeah, so as you can see, this detection is missed by the detector, and the reason for that is the face is less than 80 by 80 pixels, and if you need to detect this sort of face, you need to upsample the image. So if I change this to I guess maybe 1 or 2, it should work, I guess. And if I run it again, okay, it took more time, it took 1.22 seconds, but it finally detected the face here. And if I get rid of the upsampling argument and I set the upsample argument to 0 and I run it again, the face is missed, but it took less than half a second. It took 0.3 seconds. So this is the trade-off of speed versus accuracy in action for the Dlib Hawk-based detector. Up till now, we have been looking at machine learning based face detection methods, and all of them have their own limitations. For example, Haar Cascade based face detection methods can't detect faces when they are tilted or oriented, and Hawk based facial detection methods take a lot of time when the faces are in smaller scale. And even these methods can't detect faces properly. For example, take a look at this example. So there is a limitation, obvious limitation, when you're working with machine learning based methods. Now we're going to take a look at a deep learning based method. For that, we're going to be using OpenCV's DNN module. Now I will be making a separate series on that module. At the moment, I do have a blog post series that introduces this module. And this is a very interesting deep learning based module that allows you to use a number of deep learning based models like age detection, gender detection, image colorization, and whatnot. So right now, I'm just briefly going to go over how you can use this module to load up a face detection model and use it. So for that, what you need to do is first use this method cv2.dnn.readnet from cafe. Now you pass in a proto.txt file like this, and you can pass in the cafe model like this. So in OpenCV, you can't train deep learning models, but you can use deep learning models that were trained on a different framework. For example, Cafe is a popular framework that you use to train deep learning models. So you can use models that were, trained on Cafe in OpenCV. Similarly, you can use models that were trained in TensorFlow or PyTorch inside OpenCV. There is a few catches, but I don't want to go in those details. But to use Cafe model, what you need to do is use this function readnet from Cafe, and to use a TensorFlow model, we also have a TensorFlow model when you download the source code. So you use this function readnet from TensorFlow, and then you just pass in the model name, and then you pass in the config file. The config file is different for TensorFlow. For TensorFlow, you use .pbtxt. Now this config file holds the architectural information, so how the layers are structured and how the whole architecture works. And then inside this Cafe model, this is the main model that holds all the weight files. So this is the parameters. This is the numbers that which the image will be image pixels will be multiplied with when it passes through the network. So this is the file which will be the most heavy. It will be in several MBs. And similarly for TensorFlow, this is the main weight file. So OpenCV face detector unsigned date.pb. This is the file that will be the largest, and it will be several MBs in size, because this file contains all the weights of the parameters that the model has after it was trained on the dataset. So anyways, right now I'm going to show you how you can use the Cafe model. Similarly, you can uncomment this when you download the source code, and you can use TensorFlow model instead. So after loading up the model, you're going to see something like this. And then what we need to do is we'll create a function cv_dnn detect faces, passing the image, passing the loaded DNN model, and I'm just going to define a certain minimum confidence, so 50%. Anything below that, I'm not going to consider that as a valid detection. Display set to true. And then what I'm going to do is before you pass in to the detection, you need to pre-process the image. So for deep learning, this is a common practice. You pre-process an image before passing it to the model itself. And then after the results come back, you post-process the results and extract the things you want. So for the pre-processing, OpenCV already has a function for that. So cv2.dnn.blob from image. Now this function will take care of all the pre-processing that is required. And for this particular model, the pre-processing that we need to do is we need to scale, we'll have a fixed scale factor of 1.0, which doesn't scale the image. Normally, you have this number like 1 divided by 255, which normally rescales the image and divides it by 255. This is a common pre-processing scheme that some authors of the papers use. Now for this model, we're not gonna do that. And here we're gonna resize the image to 300 by 300. And then we're going to subtract this mean values. This is the mean RGB values. So it's a common practice, like for some authors that they normally do is that they calculate the mean RGB of the whole data set and then subtract those values from every image. This greatly impacts the accuracy and the training, like the training time and things like that. So this is the mean values for this particular model that we need to subtract. And this is a variable which tells the model to swap the RGB channels or not. So when we are working with TensorFlow, the TensorFlow library normally works with RGB images, right? So for that, because you loaded the image in OpenCV and the image will be in BGR. So if you're working with a TensorFlow model, you need to set this swap RGB to true. Because when the pre-processing is happening, the function needs to, swap out the red and blue channels. So the BGR image is converted into RGB before calling the TensorFlow model on it. So if you don't do that, you will see a decrease in accuracy because the model will be trained on RGB images and you're passing in a BGR image. And then this is a center crop. This will be false. Sometimes the author center crops the image, and if they do that, they will specify in their docs. So this is the information that we get from those docs. So OpenCV already has listed in this model repository, it has listed out a few models and it's parameters that you need to specify. Like I said, I have already created a 3-part series specifically on DNN. I'll be making a video series on top of that, so to cover this whole DNN thing in detail. It's really interesting and it allows you to do a lot of things. Anyways, since one thing I did forgot to mention, that Caffe model, the Caffe framework works in BGR, so we don't need to swap out the channels. That's why I'm setting it to false. So I don't need to swap out the channels because Caffe itself trained on BGR images. So once we have a processed image, which will be a 4-channel image, and the extra channel is added because it allows you to work with batch images. So batch images allows you to make batch predictions. Anyways, you don't need to worry about it. What you just need to understand is that once you get the pre-processed image, all these things specified here will be done to this image, and it will also have an extra channel. Now that you have set the input for the model, you can call the forward pass function, and this is where all the processing takes place. And the model, if the image comes into the model and it goes through all the network layers, and out comes the predictions, and the predictions are stored in this results object. And now you need to post process this results object to extract those predictions, those bounding boxes, and all the related stuff like the confidence, etc. So now what we're going to do is iterate over all the results, grab the faces. So if there are multiple faces detected, there will be a lot of faces, and for each face we will get the face confidence, and then after that we will check if the face confidence is higher than some certain threshold that we're defining. Right now I'm setting the minimum confidence as 50%. So if only the face confidence is above 50% threshold, only then I'm gonna draw out the face bounding box. Otherwise it may be a false positive. So right now I just set this to 50%. You can set it to a lower value if you want. So after that, what I'm going to do is extract the bounding box, and then from the bounding box, I'm going to extract the x1, y1, x2, y2 variable. So these are the 4 points that you need in order to draw out a rectangle like this. And by the way, if you see this, I'm also multiplying these values by the width or the height, because when you get these x1, y1 coordinates, this will be in the range of 0 to 1, and you need to rescale them back with respect to that image. And for that, you need to multiply the x coordinates with the image width and the y coordinates with the image height. So that way you get the actual coordinates and rescale them back to from 0 to 1 range to their actual range. So once that is done, all we need to do is just draw out the bounding box, and here we just optionally annotating the image with their, like the confidence value. And I'm just rounding up the confidence value with the range 1 to 10. So you'll see a number here telling you how confident the model is regarding that prediction. So anyways, once that is done, I'm going to display the results, and otherwise I'm going to return the results if I'm working with videos. By the way, if you're wondering how did I knew if this, like how I'm iterating through these variables, for example, how did I know to pass in a 0, 0 here, or 2 here, or 0, 1, 2, 3 here. So this is easy if you print out, like this results object and see the NumPy array that comes with it. So once you analyze that NumPy array, you will know which variable is returning which thing. And there's also docs for each model. There are sometimes relevant docs associated with it, which will help you get the required variables, extract required variables from the returned result object. Anyways, there's that. So once we've done that, I'm going to initialize this function, and I'm going to pass in a sample image and call this function on it. So so see this image was missed by the Haar Cascade function, and right now it's accurately detected with 100% accuracy. It's not exactly 100% because I'm rounding it out, so that's why you're seeing 1 here. And the time is pretty fast, 0.03 seconds. It just took 0.03 seconds to find the face and draw it out. And for this image, I think there's a issue with that. I think, yeah, all right. I know what happened here. Okay. So yeah, accurately detected 0.02 seconds. And another image. Yeah, even though there is a mask present here, the face is correctly detected and drawn out. So this is the OpenCV's DNN. It's one of the best methods to do face detection when working with OpenCV. Well, I think when working with OpenCV, it's the best one, but generally speaking, it's one of the best one to use in Python. Oh yeah, one thing that I forgot to tell you was the OpenCV's deep learning model that we just use is basically an SSD plus ResNet model. So an SSD is a very popular single shot detection framework, which is a detection architecture. And with a detection architecture, normally you have a base model, which is a classification model. And for this particular detection scheme, we're using a ResNet variation, a Res10 model. So using a combination of SSD plus ResNet model allows us to achieve a very high accuracy with a relatively fast FPS. So that is it for this model. Let's take a look at the next one. Now the next model is this one, Dlib's deep learning based face detection. Now this model is more accurate than the Hawk based face detection model that comes with Dlib. But here's the issue. When you're using this model, you need to make sure that you're using the NVIDIA GPU. So because this model will be really slow when you're working on a CPU. And this model is ideal when you have a GPU and you need to utilize that. And here's a release page from Davis King regarding this model. So this model is actually called a maximum margin object detection. And it's a detection scheme. Davis King also published, I think, a paper on it. So here's the paper describing this maximum margin object detection pipeline. So how this works. And here's the difference between this model and the Hawk plus SVM model. The major difference is that the Hawk plus SVM relied on Hawk-based features. Now, Hawk-based features are really accurate, but when the rise of deep learning came, we have more robust feature extractors, specifically CNN, convolutional neural networks. And these deep learning based CNNs were really more powerful than the Hawk based feature extractors. So that is why this combination of CNN for feature extractors plus and maximum margin object detection scheme, the combination of this is a lot more accurate than the Hawk based SVM scheme. And I think there is a comparison between both of those models. So here is a comparison of the Hog based face detection model plus with the deep learning based CNN maximum margin detection model. So in blue rectangles, you will see the results of Hog based model, and the red rectangles will give you the results of the deep learning model. As you see, the faces are faces that are occluded, that are sideways, are also really accurately detected by this deep learning based model. And a lot of these detections are missed by the Hog based model. So all these 6 images, the Hog based model was run on all these 6 images as well as the DNN model. But as you can see, most of the detections are mostly missed by the Hog model, specifically those which are occluded, which are sideways, which are far away and stuff like that. So as you can clearly see, the CNN model is a lot more accurate than the Hog based model. But it comes with a major disadvantage that you can't use it on a CPU. You can, but it will be tremendously slow. I can show you how slow it is. So here I'm loading up the model, and the syntax for the whole thing is same, pretty much the same. All you need to change is this dlib.cnn face detection model v1, and you pass in the model path. This will be an external model. This doesn't come with the Dlib library, so you will have to have this inside your PC and pass the path to it. So here I have this model inside my models directory, mmod human face detector.dat. So this is the model's name, and once I've loaded up the model, it's here. And all I need to do is just use the same script which I previously did, call up the, read up the image, resize the image, and then I'm going to convert the image into RGB, and then I'm going to pass into the CNN face detector. I'm going to set this to 0. I'm not going to upscale the image. It's like I said, it's tremendously slow without the upscaling. If you upscale, then it's going to take, I don't know how long. Anyways, once you get the results, you iterate, you get the bounding box, you extract x1, y1, x2, y2 coordinates, you draw the rectangle up, and then you display the results. It's the same syntax that we used for the Hog based method. So I'm going to initialize this function, and then I'm going to check it out on some images. It's going to take us some time. It's still running. So as you can see, it took 4.3 seconds to detect this face. And one of the issues that I have with this model is that the faces that are, detected and drawn out are not actually, centralized. So the face will always be on top. And the chin will be left out. I don't know why is that. I think this is because the annotations for this dataset was done in that way. So as you can see, the chin is always, below the bounding box. You can, I guess, readjust by applying a constant padding so that whenever the box is detected, the chin, is covered. So as you can see, the chin is left out, But other than that, it's really accurate. But the con is that obviously it's taking a lot of time. And because I'm using a pre-compiled Dlib library, I can't use my NVIDIA GPU, which is in my PC right now. But if I, install it from source, and because I'm using Windows, it's somewhat little hectic, but I can get around that. Once I do that, I can leverage the NVIDIA GPU with this, and then it will be really fast and it will work in real time. But you will be relying on a GPU. So that is a con, but the advantage here is that it's really accurate. All right, this is the final face detection model of the day, and it's arguably the best one. So here what we have is this Mediapipe's deep learning based face detection. It's based on this face detection model, and there's a paper for that here. And as you can see by the title, Blaze Face sub-millisecond neural face detection on mobile GPUs. It sounds pretty interesting, and it actually is. So this model is actually really fast, almost 200 to 1000 plus FPS on flagship phones. All you need to do is just initialize this function MP face detection equals to MP solutions dot face detection. And once that initialization is done, just set up the function by doing MP face detection dot face detection model selection equals to 1, which specifies which model to use. There are two models, 0 or 1. By default, I think it's 0. And this selection depends upon the range. If you want a short range model for up to 2 meters, you use this one. And if you want a longer range one, you use the other one. So once you do that, there's another variable which you can also specify. This is the minimum detection confidence. So right now I'm setting it to 40%. This is the same minimum detection confidence that I was setting up when I was doing the SSD plus ResNet function model in OpenCV. So for this model, it's set up here by default. So you use just 0.4. I think it's by default it's 0.5. Yeah, the default value is 0.5 for this one. So anyways, I'm also doing this MP drawing equals to MP solutions dot drawing utils. This will allow me to draw out the phase detection. I can also do that with OpenCV, but there's another utility function that you can leverage that comes with Mediapipe. Anyways, so after the initialization is done, I'm going to create this function called MP detect faces. And here I'm going to do all the pre-processing and post-processing and return the results. By the way, with phase detection, by using Mediapipe, you also get this. So these are some key landmarks on the face that you also get with Mediapipe's phase detection. So it also tells you where is the right eye, left eye, nose tip, mouth center, right ear and left ear. And by my experience, these coordinates are not that accurate, but it's an extra that you get with Mediapipe's phase detection method. So anyways, there's that. And to run this model, what you need to do is just convert the image from BGR to RGB, because Mediapipe accepts images in RGB format, and then you pass this RGB image in this function MP face detector dot process, and all the processing happens in this line of code, and you get this results object. So once you get the results object, what you need to do is check if the faces were detected, if any faces were detected. So you do that by doing if results dot detections, and if any face were detected, you iterate over all possible face detections by doing this results dot detections. And then what you do is call this utility function, which we initialized earlier, MP drawing dot draw, and this will draw out the whole any possible faces that were present in the image. So any faces that were present will be drawn out using these specifications, the color, the thickness, the circle radius, etc. So this way we are using Mediapipe to draw out the faces, but similarly you can use OpenCV to draw the faces as well. So for that, what you need to do is extract the x1 coordinate or the y1 coordinate, and you can do that by doing face box dot xmin and dot ymin. This will give you the x1 y1 coordinate, but you need to multiply it with the image width and the image height. So because initially these will be ranged to 0 to 1, and you need to get the actual coordinate value, and for that you need to multiply it with the width or height. So you can get x1 y1 that way. And similarly, there's another attribute that you can call is its width and the height. So when you do that, you can also extract the width and the height, and then you can add the width and the height to these coordinates to get the x2 y2. And after that, you can use cv2.rectangle to draw out those rectangular boxes. But right now I'm just drawing out the boxes using this function. I also have this, and this is just to draw out a nice box background to display the confidence value on top of the rectangle, just for display purposes. That's there. And then if the display is set to true, I'm just displaying out the results, and if it's false, I'm just returning the results in case I'm working with videos. And once that is initialized, I'm going to show you the results on a couple of images. So for this particular scenario, as you can see, the faces are oriented at different scales, and we have the boxes drawn out here along with the landmark coordinates like this. And as you can see, the landmarks are not that accurate, but still, I mean, it's you're getting these for free. So there's that. So yeah, these are the results for this one. And see, even though the face is occluded with this here, the ROI is quite big enough, and it's covering the chin, it's covering the side cheek, and all those other hidden areas. So Mediapipe's face detection is getting around those obstacles here. And let's check it out on another image. Very accurately detected. And one last image, and yeah, so yeah, it missed out this one. I think it's because this one was somewhat blurry. So yeah, but it accurately covered this one, and the landmarks are drawn out neatly enough. Anyways, now that we have gone over all the 5 methods on images, let's take a look at a function which I've created here. And this function is just like storing all the names of all the 5 methods in a list. And if I press the S button, the list will be appended by this variable. So I'm going to append this variable by 1, and I'm going to iterate over all of these models by pressing an S button. So, and if the model algorithm is hog, then I'm going to call the hog method. If the algorithm is OpenCV DNN, I'm going to call this method. Similarly, I'm going to call any of the above methods by going through this list, and I can do that by appending this, incrementing this variable algorithm index. So it's a really simple script. I've just created this to test out each individual model by just pressing through a single button. Now let's test it out. I'm going to run this cell. I'm going to see the results in real time for all the models except this one, Dlib's DNN, which is going to be tremendously slow. So as you can see, I'm right now running the Mediapipe's face detection. It's really fast and it's pretty accurate. There was a false positive just now. You can get rid of those by increasing the confidence a bit. So I might increase the confidence and I can get rid of those false positives. So let's shift to another one. And yeah. So this is OpenCV's DNN model in action. It's a little bit slower in FPS compared to Mediapipe, but still pretty fast in real time, really accurate. And yeah, it's detecting sideways poses too, as you can see. And this is the hog. It's somewhat slower. The FPS is slower, but it can work with real-time applications too. And it's detecting somewhat poses, but I guess it might fail if I, yeah, it's okay. It's pretty good actually. So now let's check the Haar Cascade one. Yeah, faster than the hog-based model, but as you can see, it's introducing false positives here and there. You can again tune these values, maybe reduce the false positive for this particular scenario. But in general, you need to tune the values in order to get this working perfectly. And the Haar Cascade fails, when I shifted the side poses. Anyways, yeah. So this is the lowest least accurate model. And now when I press the S button, it's gonna show you the Dlib's DNN model, which is gonna be tremendously slow. And for that reason, the screen is gonna froze up, and you're gonna see the screen freeze when I press the S button again. So yeah, the screen is frozen right now, but I'm still there. So this is the issue with Dlib's DNN. It's gonna be, like I said, extremely slow, and so there's an issue with that. So anyways, I'm gonna close up this by pressing the escape button. Okay, all right, yeah. So yeah. So here's another demo of a man where I'm running all of the 5 models on the same video. I've recorded these videos separately, and now I've stacked to show you the results for all 5 of them at once. So here's the big question. Which face detection method should you actually use? So here's a quick guide for that. Use Haar Cascades if you want a quick, simple setup and a fast real-time solution. But if you want something more, if you want to detect faces that are tilted, that are oriented, then go for Dlib's hog plus SPM based detection. And if you want something more accurate and more robust and you have a GPU, then you can leverage the Dlib's CNN plus MMOD maximum margin object detection method. But the disadvantage here clearly is that you can't use it on a CPU. But if you want a really accurate, robust detection, but you don't have a GPU access, so what you need is OpenCV's SSD plus ResNet detection model. It's extremely accurate and it's really fast on a CPU. But the best combination that you can get in terms of accuracy and in terms of speed is with Mediapipe's Blaze face detection model. It gives you the best speed and accuracy trade-off. Plus, it's really great for running on mobile devices and other platforms like the Edge or the web. So it has bindings for that too. So it's excellent for cross-platform development as well. Here's a bonus tip. A few years back, I actually published a library called Bleed AI Face Detector. So this is called bleed face detector. You install it by doing pip install bleed face detector. It's in pip, as you can see here. And this allows you to use 4 face detection methods. So all of the 5 which I just went over besides the Mediapipe one. So besides the Mediapipe one, all of the 4, the rest of the 4 implementations are in this library. And it's a really simple code. So with just 5 to 7 lines of code, you will get the face detection running. And to choose a different model, all you need to do is just change this line of code. You just need to change this single line of code and you can use 4 different face detection methods. And all you need to install is this library, Bleed AI Face Detector. So this is just a bonus tip for this tutorial. So that is it for this tutorial. I hope you enjoyed it. If you did, please let me know in the comments and do like this video and subscribe to my channel. That is it. I'll see you next time. Bye.